Welcome to Industrial Problem Solving.
My name is Dave Roytsum.
This is a continuation of a mini-series on troubleshooting web manufacturing and converting issues using the best practices of traceability. Please see the 5 earlier clips if you have not already done so. In this clip, we discuss the permanent damage that can sometimes happen during storage. In the next clip, we will cover transportation damage. The first of 2 key concepts for storage sorrows is the difference between elastic and plastic behavior. Elastic behavior is the most common and the simplest to understand. Elastic means there is no permanent changes for a roll just sitting in storage. Elastic means that the roll has no memory of being stored. Most importantly, elastic means that if the roll goes in good, the roll will go out good. Plastic behavior, on the other hand, is much more complicated. What happens depends on time and on rheology and other factors. Please don't get stuck. The most important thing here is to not complicate problems more than they need to be for any particular issues you are working on. Elastic behavior is the most common. The easiest test for many plastic behaviors will be for time dependency. The next key concept is that many processes, including those in manufacturing and converting and storage, are TTP problems. TTP stands for time, temperature, and pressure. However, for all paper as well as some other materials, moisture acts almost in the same manner as temperature. For rolls in storage, internal pressure is the pressure between the layers that varies from high near the core to 0 on the outer wraps, as we taught in our award-winning and trademarked Web 101 class that has been taken by 5,000 students. No less important is external pressure due to gravity and handling. If there is time-dependent behavior, then you will need to know the time constant, which can be seconds to years for many converting processes. The time constant is the amount of time it takes to get to 63% of its final value. In this graph, we show one system that starts at a value of 10 and another system that starts at 0. Yet, they both tend to an equilibrium of 5. And also, the time constant for both is 1. So, for example, this could be a shipping roll of paper that has an initial moisture content of 10% that in 1 year's time will equilibrate to about 5% in dry storage without a wrapper. This could also be the response of the film web temperature as it rises upon entering a dryer, and this will happen in a matter of seconds. Yet, this could be any time-dependent material or parameter. The next key concept is that often these parameters are interchangeable over a region of practical interest. For example, more time in storage at cold temperatures may be equivalent to less time in storage at hot temperatures and vice versa. Another example is that there is more distortion of a roll in storage due to interlayer pressure at hot temperatures versus cold for a given time. Other of the many examples of interchangeability in common converting processes include drying speed and drying temperature, or calendaring speed, and calendaring pressure. Here is an example of wound roll blocking that we cover in more detail in my award-winning and trademarked Web 101 class. We showed that the physics of winding guarantees that blocking will be worse at the core than elsewhere because the interlayer pressures are greater there. However, blocking is equally, if not more, responsive to time and temperature and chemistry of the substrate and chemistry of the two surfaces. In short, winding is only a small part of the physics of this blocking problem. Here is another time-dependent mechanics covered in our Web 101 class. That is, rolls going out around in storage. This problem, of course, depends on winding tightness. However, it also depends on time, and it also depends on temperature, and it also depends greatly on how the rolls are supported in storage. The time constant for rolls going out of shape may be a few minutes to a few months, depending on the chemistry. Almost always, temperature effects are reversible. In other words, cooling down from room temperature and then warming back up to room temperature would bring interlayer pressures back to where they started. However, I have been involved in cases where a single exposure to cold caused a permanent loosening of the bottom of the film rolls. Another example is moist roll in dry storage loosen the outside wraps of paper rolls. Both of these examples are contrary to expected simple physics. In the film example, we would expect to tighten, not loosen, the film rolls down near the bottom due to thermal contraction against an unyielding core. However, there are irreversible strain changes on this curious film that are on the order of parts per thousand. Still, small strains can have a huge effect in web handling. Similarly, we would expect that the outer layers drying out on a paper roll should cause it to get tighter. However, paper can have a higher ZD contraction rate due to moisture reduction than its MD reduction. Behaviors like this and many others require us to go into the literature to search for rare studies of uncommon physical properties of our materials. You can calculate and model and measure moisture and temperature changes on rolls in storage using the methods I wrote about 25 years ago and teach to this day in my Web 101 class. We even have a simple app to do this. Here are the moisture or temperature contours on a cross-section of a wound roll as it moves to equilibrium. In the 1,000 plants I've worked in, I've seen countless examples of truly odd behavior. Here are a few more. First, many materials get slipperier with time. Thus, the risk of telescoping at your customer may increase. Wound rolls with fluids between smooth layers are at risk for oozing the fluid out the edges with time and, in the process, will risk loosening of the wound roll. If the material is smooth film and the fluid is air, you can get the classic air buckle as shown in the picture. Another odd problem I worked on in paper was it literally rained inside the packaging due to temperature swings and the consequent change in relative humidity for the air inside the package. Not everything about storage is bad, however. Perhaps the most important is that inventory is a buffer between two manufacturing processes that have differing rates of production and consumption. This will help prevent the just-in-time from becoming just a little late. Some other examples of the utility of storage that I don't know of include paper, where the moisture streaks level out with time, and the tendency for less winder vibration. Perhaps you have encountered some surprising high-order behavior in your troubleshooting travels. If so, please share here in the comment section below or email me. Thank you so very much for joining me in this problem-solving and problem-preventing process.
This clip included some complicated high-order behavior that you may find in your troubleshooting travels.
In the next clip, we will discuss the troubles that can happen while handling and transporting rolls. If you found anything interesting or useful here, please consider supporting the work of this channel using the Patreon link below. Patreons are given special thank you gifts ranging from email help to a signed copy of my latest book, the must-have 500-page web handling handbook. See you next time.